Okay, so at this point, you are probably needing to hear me go back over all of the information about quantum numbers that we discussed today in class. So I'm going to just kind of go through and focus on each individual word and give you some examples of each, and you'll probably want to watch the second tutorial where I go through and work the orbital notation of a couple different elements. So we've got four quantum numbers, and that first one is n. And this is definitely the easiest one to think about because the higher your value of n, the more energy it has. So, for example, something that has a principal quantum number of 1 has less energy than something that has a principal quantum number of 5. And the key thing to remember, if you're looking at your periodic table, these correspond to those periods, those rows that we talked about yesterday. So we know that this is period 1, period 2, period 3, period 4, period 5, 6, and 7. Okay, so each one of these, we now see that as we go down a group, our energy is actually increasing. So theoretically, you could have a principal quantum number of anywhere from 1 to 7. So for n could equal 1, 2, 3, 4, 5, 6, or 7. And again, as that value increases, the energy is also going to increase in that those electrons in those outer levels have a lot more energy. The second principal quantum number is that subshell, and this is where you have to understand that Bohr's model, think of this as the nucleus, talks about those energy levels. So that would be energy level 1, energy level 2, energy level 3, so on and so on. But within each energy levels, there are sublevels or subshells. And that is where this angular momentum quantum number comes from. You've got four possible subshells, that we will talk about in honors chemistry. And they are given a value of 0, 1, 2, or 3. If it's looking at the first subshell, that represents S. The 1 represents the P subshell, and 2 represents the D subshell, and 3 represents the F subshell. We are going to talk a lot more about these when we move to electron configuration, but for right now, just kind of remembering that S is a sphere, P is like that infinity, some people would call it a dumbbell, D is a clover leaf shape, and then F is actually a double clover leaf, which is really hard to show you on a 2D piece of paper. So it can have any of those values 0 to 3. Next up is the magnetic quantum number, and this is where we're going to start talking a little bit more about the word orbitals. Over here, each one of these sublevels, so here's the energy level, we think of this as n equals 3, get that down, sorry, n equals 2, and n equals 1. Within each one of those energy levels, you have sublevels. So for example, in the first sublevel of S, it has one orbital that can hold 2 electrons. The P sublevel or subshell has 3 orbitals. Okay, each one of those is called an orbital, and it's a location where 2 electrons can exist. So the P sublevel can actually hold a total of 6 electrons, and those little arrows that I'm putting in there are representing electrons. The D sublevel can hold a total of 10 electrons. It actually has 5 orbitals here. So it can hold 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10 electrons. And then the last one is the F sublevel. It can hold 14. It has 7 orbitals, 3, 4, 5, 6, 7. Each one of those represents an orbital, again, where 2 electrons can exist. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, and 14. And at this point, for Honors Chem 1, that's where we stop, is at that F sublevel. But understand that there are more sublevels. So to understand this in terms of magnetic quantum quantum number, you have to understand the term orbitals and that each one of those is an orbitals. And we actually have numbers that we can assign to those. So looking at the s sublevel, it has one orbital, and that is the 0 orbital. That's its numeric value. The p sublevel has 3 orbitals, and they range from -1, 0 to +1. The d sublevel has 5 orbitals, as we just talked about earlier, and that ranges from -2 all the way to +2. And then the last one, the F, has 1, 2, 3, 4, 5, 6, and 7. And you might be starting to see a pattern here. They are going to range from -3 all the way to a +3. The magnetic quantum number has to do with what orbital it is in. And that's looking really, really, really specific, but I do want you to understand that you've heard the term before, so that whenever we get into Honors Chem 2 next year, you will have at least been exposed to this information. And then the last magnetic spin quantum number is very simple. If you think in terms of these arrows that I put up here, electrons, and you're going to learn tomorrow, that they always spin in opposite directions. Okay, so you're never going to have, if this right here was an orbital, you're never going to have 2 electrons spinning in the same direction. It's not going to happen. They are always going to spin in opposite directions. To represent that first electron, we write it as a +1/2. To represent that second electron, we write it as a -1/2. And that again is just to represent that spin on it. So this is kind of an overall description of those 4 quantum numbers. Again, the top 2 are definitely the more important 2 quantum numbers that you need to be familiar with. The bottom 2 would kind of be looking at a bonus problem, something that you would be exposed to a lot more in honors chemistry. And in the second tutorial, I'm going to explain how to work through a couple of quantum problems.